So this is ELC 131, Circuit Analysis 1, and the topic is sources of electricity. Now, generating electricity is really all about separating charge, creating a deficiency of electrons at one point and creating a surplus of electrons at another point. Now, the first source of electricity we'll talk about is called electrostatic induction. And this is where electricity is generated through friction, or what's called the triboelectric effect, is where materials are separated and these materials have the ability to accumulate a charge. Now, you've all experienced electrostatic induction, and a good example is when you walk across a carpeted floor, and sometimes even a vinyl floor or linoleum floor. And what happens is the friction of you moving across the carpet actually creates a positive charge on your body. Humans tend to accumulate a positive charge. And if you get close enough to a point where this charge wants to be distributed to, such as a doorknob, you'll actually feel the electrons flow from your finger to that metal object, in this case, the doorknob. And if it's dark, you'll be able to actually see the spark that's created when the electrons leave the doorknob and go to your body. Now, the triboelectric effect is really a good example of that is when you pull plastic wrap off of a roll. The friction caused by the plastic wrap leaving the plastic on the roll will accumulate a positive charge on the plastic. So let's look at an example of electrostatic induction. We have a piece of plexiglass, and underneath the plexiglass are some Rice Krispies. And I'm going to rub the surface of the plexiglass with a wool sock. And the friction between the plexiglass and the wool sock will actually take electrons from the plexiglass and stick them on the wool sock, leaving the plexiglass with a positive charge. So let's make some friction. There we go. And you see that the positive charge on the plexiglass attracts the Rice Krispies, which have no charge, and the charge dissipates over a period of time, so you can see the Rice Krispies fall back off. Now, whatever electrons we've pulled loose from the plexiglass are distributed onto the sock. However, the sock quickly releases those electrons to the surrounding air molecules. Continuing on with the discussion of electrostatic induction, we'll look at an example of the triboelectric effect. Now, when I pull cellophane tape off the roll, this cellophane tape will accumulate a positive charge. And two pieces of cellophane tape, both having a positive charge, these pieces of tape will repel from one another. So see how they get close together, they actually push apart. And this is because they're similarly charged bodies. So another method of generating electricity is the photovoltaic effect. And this is when the radiant energy of light strikes a semiconductor material and it causes electrons to migrate from one region to another. For example, we see here an incandescent bulb, and this incandescent bulb is generating photons, which are particles of light energy. If this photon strikes an electron, it knocks that electron loose. We've talked about this earlier. If we add energy to an electron, it leaves its valence orbit. And what happens is that electron migrates from one side of the semiconductor material to the other side of the semiconductor material, therefore creating a charge differential from one side of the semiconductor material to the other side of the semiconductor material. So let's look at an example of the photovoltaic effect. Now, we have here what most people refer to as a solar cell, and I've had the solar cell or the photovoltaic cell connected to a voltmeter. And we can see that when we connect the voltmeter to the output of the solar cell, we're now getting approximately, well, 0.79 volts with room light striking the photovoltaic cell. Now, if I add more incident light with a flashlight, notice that the voltage increases because there's more photons striking the electrons in the semiconductor material, hence causing a greater charge differential or a greater voltage. So another way of generating electricity is through electromagnetic induction. And this is where we generate electricity through relative motion between a current carrying conductor and magnetic lines of force or a magnetic field. Now, if we look at the sketch on the board, we've got a permanent magnet here with the poles south to north and another permanent magnet with the poles south to north. And existing between these magnets will be magnetic lines of force. And above this, or these lines of force, we have a piece of wire or a conductor. Now, if I move this conductor down through the flux, that motion of the conductor moving through the flux will generate a voltage in this conductor. And this will actually generate a voltage that will be positive to negative. Electromagnetic induction is how the majority of the electricity in this world is created. We move a conductor through magnetic lines of force, and it's interesting when we talk about, or when I ask students, how do we make electricity? A lot of people will say nuclear, or they'll say coal, or they'll say wind turbines. They're all the same mechanism of generating the electricity. It's just that the energy used to move the conductor through the flux is different. In some cases, this motion is caused by the steam from a nuclear reaction that turns a turbine that makes the conductor move, or it's the wind blowing on the blades of a wind turbine that causes the conductor to move through the magnetic field. It doesn't matter what the source of energy is, the means of generating electricity are the same: electromagnetic induction. So let's look at an example of electromagnetic induction. We have here a coil of wire, and connected to the coil of wire is a metering device called a galvanometer. And the galvanometer allows us to measure voltage in both a positive and a negative direction, with no voltage applied, as you can see the pointer's right in the very center. Now, electromagnetic induction involves relative motion between a current carrying conductor and magnetic lines of force or flux. So as this magnet moves towards the coil, notice we have deflection in the positive direction. Now, when the magnet moves out, notice we have deflection in the negative direction. We only have a voltage when there's motion relative to the magnetic lines of force and the current carrying conductor. So only when the magnet moves in or out do we induce a voltage or generate a voltage in the conductor. And of course, as you can see, the polarity of the voltage, positive or negative, is determined by the direction of motion between the magnetic lines of force and the conductor. Now, we see here as another example of electromagnetic induction, a DC motor. And the DC motor is connected to a voltmeter. Now, a DC motor and a generator are really the same thing. With a motor, we apply voltage and it causes the shaft to rotate. With a generator, we rotate the shaft and it generates electricity. So as I rotate the shaft of this motor, notice I get deflection in the positive direction. Now I'm only generating voltage when there's motion, when the conductors are moved around inside of a magnetic field. The faster I spin the shaft, the greater the voltage. So electromagnetic induction involves relative motion between a current carrying conductor and magnetic lines of force. So another means of producing electricity is through the Seebeck effect. And this is where we apply thermal energy to the junction of two dissimilar metals. Now, we see an example here of a circuit device or a circuit element that we call a thermocouple. And this particular thermocouple is a type J thermocouple, and they are widely used in the branch or field of electronics called instrumentation. Now, the type J thermocouple has one metal is iron and another metal is an alloy called constantan. Constantan is made up of 55% copper and 45% nickel. Now, when we apply thermal energy to this junction of the two metals, what we find is that electrons migrate through the junction. The electrons leave the constantan and flow into the nickel. Nickel has, or excuse me, iron. The iron has what we call a higher electron affinity than does the constantan. Now, if we have electrons leaving the constantan and flowing into the iron, we'll find a voltage differential across these two terminals, positive to negative. Now, the Seebeck effect, again, is when we apply thermal energy to the junction of these two dissimilar metals, and it causes or creates a charge differential across the two metals. What's sort of interesting about this junction of two dissimilar metals is that if we were to apply a source of energy to these two materials, then the current flow from this material to this material would actually cause one side of the junction to heat up and cause the other side of the junction to cool down. And this is called the Peltier effect. because we can't have it work one way without working the other. If applying thermal energy to the junction makes a charge differential, forcing current flow through the junction has got to generate thermal energy. We can't have it one way without having it the other way. So let's look at an example of the Seebeck effect. This device right here is a thermocouple, and this is a type J thermocouple made with a junction of uh, iron and constantan. And at room temperature, you can see that the thermocouple is outputting a voltage. It's 0 volts. It's too small to measure with our measuring equipment. However, when we apply thermal energy to the junction of the dissimilar metals, notice that we're able to get, what are we at now? 30, almost 40 millivolts from this thermocouple. It's gotten all the way up to 42 millivolts. And as the thermocouple cools back down, you'll see that the voltage falls back to 0. Another device that makes use of the Seebeck effect is this device, and it's called a thermoelectric generator. Most everyone simply refers to it as a TEG for short. Now, the thermoelectric generator is constructed with two ceramic plates, and in between the ceramic plates is a semiconductor material. And with this device, the semiconductor material in between the plates is boron. Now, when we connect the voltmeter to the output of the thermoelectric generator, notice that we've got about 14, 12, 10, 9 millivolts. And the reason this voltage is dropping off is that the device generates an electricity due to the differential of temperature between the two plates. So when I put my hand on the top plate, notice that the temperature increases because now the top plate is, of course, warmer than the bottom plate. And if I take my hand away, you'll see that the voltage starts decaying again. If I turn the device over and heat this side, now you'll notice that the voltage goes negative. And these are very interesting devices because they can be used to generate voltage in situations where you simply don't have access to any other source of electricity, such as when you're backpacking. You have to be very careful with the tags because the plates are ceramic material. They're very brittle. You have to be cautious when exposing them to direct flame because the ceramic may crack. But we see wide use of these devices to generate voltage in situations where there is no other source of voltage. So another means of or method of producing electricity is through the piezoelectric effect. And this is where stress placed upon a crystalline material causes a difference in potential or a charge separation across the crystalline material. And this crystalline material could be quartz, it could be Rochelle salts, it could be some man-made crystalline materials, and as a matter of fact, it can even be cane sugar. Now, what happens is that if we place some force upon this crystalline material, here's some force down upon this crystalline material, what happens is that the molecules inside the crystalline material are compressed, forcing electrons to move to one side of the crystalline lattice structure inside the material, and a deficiency of electrons exists at the other side. And this will create then from one side to the other a charge differential or a voltage. And the voltage that's generated is directly proportionate to the amount of force. Now, some of you might not be quite old enough to remember record players, but with a record player, what you had was a needle connected to a crystalline material. And as the needle went through the tracks of the record, this caused the needle to move this way and move this way and move back this way and move back this way, causing this crystalline material to be twisted this way or this way or this way or this way, generating then from the sides of the crystalline material a voltage that changed from positive to negative to positive, which would recreate the audio information that was used to create these tracks. So let's look at an example of the piezoelectric effect. What we have here is the crystal that was taken out of the inside of an oscillator, a crystal oscillator, such as that would be connected to your CPU. And all we did was just cut the oscillator apart and get the crystal out. And notice that as we stand right now, there's no force applied to the crystalline material, so there's no voltage. But when I depress the crystal or press on the crystal with the pen, notice that the voltage increases, and as the force goes away, as the crystal goes back to its original shape, the voltage goes back to zero. So as I depress or flex this crystal, notice it generates a voltage, and this is the piezoelectric effect. Now, similar to the Seebeck effect and the Peltier effect, the crystal also exhibits a similar relationship in that if I apply voltage to the two terminals of a crystal, it'll cause the crystal to deform. And if I apply force to it and deform the crystal, it'll generate a voltage. So the last means of producing electricity that we'll discuss is through chemical action. And a chemical action / reaction creates or causes a charge separation. Now, we typically think of producing electrical energy through chemical action / reaction as a simple battery. Now, in order to have a cell or create electricity through this chemical action reaction, we have to have some sort of electrolytic material. And this electrolytic material can be acid, it can be salt water, sodium chloride in solution, but we have to have some means of being able to transport electrons from one point to another point. So we'll use the example of an orange, which contains citric acid. And then we have to have, again, two dissimilar materials, or in this case, two dissimilar metals, copper and nickel. And what happens is the electrons leave the copper the electrons leave the copper and move through the citric acid to the nickel, therefore creating a charge differential between the plates or between the dissimilar metals. So a chemical action requires us to have an electrolyte, and it requires us to have two dissimilar metals to be used for the anode and cathode of the cell. So let's look at an example of chemical action used to produce electricity. So we have a lime, and what I'm going to do is put a piece of copper wire in the lime and a galvanized nail. And the galvanized nail is coated with zinc. So we'll have two dissimilar metals, and between these two dissimilar metals is citric acid that we can use to move electrons from one metal to the other. And note that we're producing 0.85, almost 0.86 volts across the two terminals of the battery that we've constructed. And you notice the voltage has increased a little bit because as the two electrodes are in the citric acid, it's cleaning some of the oxides off the surface of the metals. So the voltage actually will increase just ever so slightly. So this is an example of chemical action used to produce electricity. We have to have an electrolytic material, in this case citric acid, and two dissimilar metals, copper and zinc.